This is the first video on section 5.5, absolute extrema. And we start with the extreme value theorem. Remember, we had something called the extreme value theorem in Calculus 1 that said that a continuous function on a closed interval had a max and it had a min. Here we have something similar, except we don't necessarily just have a closed interval, we have a closed bounded region. So a continuous function on a closed bounded region has a max and it has a min. Also, what we learned in Calculus 1 is if you have a continuous function on a closed interval, the max and the min occur at either the critical numbers or the endpoints. Here, if you have a continuous function on a closed bounded region, the max and the min values occur at either the critical points or the boundary points. These problems are going to be a little bit more complicated than the ones we did in Calculus 1 and Calculus 2. In Calculus 1, we would calculate the derivative, find the critical points, test the critical points and the endpoints, and be done. Here, we'll do something similar. We'll calculate the partial derivatives, find the critical points, test the critical points and the boundary points. Problem is, we're going to have infinitely many boundary points to test. In Calc 1, we had 2 endpoints. Now we suddenly have infinitely many boundary points. So let's look at example 154. G of xy is this polynomial, and the boundary that we're given, the region bounded by this triangle, with vertices 0, 0, 1, 0, and 1, 1. This is our closed bounded region. This is our continuous function. A continuous function on a closed bounded region has a max and it has a min. We have to find those. So first of all, we'll calculate the first order partial derivatives and find the critical points. So we calculate g sub x of xy. We calculate g sub y of xy. The critical points are places where either both first order partial derivatives are 0 or one of them doesn't exist. Because g is a polynomial, there aren't any places where any of the partial derivatives don't exist. So partial derivatives exist everywhere, and so we're going to be looking for places where both of them are equal to 0. This is the easiest one to work with, the g sub y. If g sub y is equal to 0, then x is equal to negative 1. And so if x is equal to negative 1, we substitute negative 1 in for x, and we have y is equal to 2. So our critical point is the point negative 1, 2. We only have one critical point. Notice, however, it's not in the region. Remember in Calc 1, sometimes you would look for a max and a min on an interval, and you'd find the critical numbers, and not all the critical numbers were in the interval. Well, a similar thing has happened here. The critical point that we have found is not in the region. So negative 1, 2 is over here, up here somewhere. And so it's not in our region. So that means now we have to check the boundary. This function has a max and it has a min. Critical point's not in the region, so we're going to check the boundary now. We have 3 cases. For case 1 is going to be in this video, cases 2 and 3 will be in the next video. The first case we're looking at is y is equal to 0 and x is between 0 and 1. So that's a fancy way of saying this. Our points are along this part right here. Y is 0, x is between 0 and 1. So we're going to check this line segment. G of xy, if y is 0 and x is between 0 and 1, then g of xy is 3x squared. Think of it this way. We're looking at g of x 0. And so if y is equal to 0, g of x 0 is going to be 0 plus 3x squared plus 0. So we have 3x squared. That has a minimum value of 0 at g of 0, 0, and it has a maximum value of 3 at 1, 0. So g of 1, 0 is 3, g of 0, 0 is 0. This is not too hard because this is a quadratic. This is 3x squared. It's increasing. It has its minimum at 0, and it has its maximum at 1. And its maximum at 1 is equal to 3. Had this been a more complicated function, had this been something harder in terms of x, then we would have had to have gone back to our techniques that we learned in Calculus 1 and Calculus 2. But in the second video, we'll look at case 2, which is that the point is on the vertical line, and then case 3 will be that the point is on the slanted line. So we'll look at cases 2 and 3 in the next video.